Okay, so let us conclude or rather continue the discussion on compressible flows. So, from the beginning we have discussed one dimensional compressible flow, then normal shock, and then we finished in the previous session the oblique shock. Now, there are few more topics which I would like to touch upon, like the Rayleigh flow and all these things, and that pretty much is going to talk about, I mean, all the fundamental stuff which we need in further cycle analysis, all this. So, this just to move ahead, we will start with the Rayleigh flow equation. So, this is one of the topic that I would like to discuss. Rayleigh flow equation. So, this is also a steady 1D flow with heat transfer, or so this is important. Okay. So, thus quite appropriate this kind of flow, or appropriate to treat the flow in combustion chamber as a Rayleigh flow case, because where the heat transfer takes place. Now, let us put a sort of an schematic to see how we can analyze this. Let us say this is a one dimensional flow, and we taken control volume between these two, which is station 1 and station 2. This is upstream. So, all your P1, rho 1, U1, H1, and downstream you have P2, rho 2, U2, H2, and you can have Q12. Okay. So, area is so this is an constant area duct. So, that is another thing that. So, also there is no work exchange while the heat is added, which is Q12. Okay. So, that means heat goes inside, that is the direction. So, we write down the governing equations. First thing that we will write down the continuity equation. So, again this is a constant area duct, one dimensional flow. So, mass flow rate would be rho 1 is A, or in other way m dot by A is rho 1. So, we can write m dot is rho 1 U1 equals to rho 2 U2, right. Now, momentum equation, where we write P1 plus rho 1 U1 square is P2 plus rho 2 U2 square. So, these are already we have derived the equations for steady one dimensional flow at the starting of the discussion on compressible flow equations. Now, they look pretty similar. The energy equation would be slightly different, that we can see. H naught is H2 plus, so we can write U2 square by 2 equals to H1 plus Q12, which is H1 plus square plus Q12. So, this is the portion of the added heat which shows up here, and the last equation of state that we get is P1 by rho 1 T1 is P2 by rho 2 T2. Now, for a perfect gas, we rewrite the momentum equation like P1 1 plus rho 1 U1 square by P1 equals to P2 into 1 plus rho 2 U2 square by P2. So, which will give us P2 by P1 equals to 1 plus gamma m1 square 1 plus gamma m2 square. So, that is a relationship that we get. Now, thus we can get similarly for temperature relations, which are 1 plus gamma m1 square by 1 plus gamma m2 square, which is m2 square by m1 square. Now, the relationship between static and stagnation temperature, that still holds good. So, this is the relationship which, if we use this relationship back in this equation, what we can write that T02 by T01 is 1 plus gamma m1 square by 1 plus gamma m2 square. So, this is whole square into m2 square by m2 by m1 square into 1 plus gamma minus 1 by 2 m2 square by, so this there is a square. So, 1 plus gamma minus 1 by m1. So, that is a sort of an little bit messy relationship, but that follows the standard equations that one can use and derive those things. So, now the similar way one can get the total pressure and the static density ratio. Let us say similarly the total pressure and static density ratio that can be expressed. So, the P02 by P01, this would be 1 plus gamma m1 square by 1 plus gamma m2 square, which is 1 plus gamma minus 1 by 2 m2 square, gamma minus 1 by 2 m1 square, gamma by gamma minus 1. So, that is what you get for the pressure stagnation pressure ratio, and static density like rho 2 by rho 1, they would be written as m1 by m2 square into 1 plus gamma m1 m2 square by 1 plus gamma m1 square. So, you get the static density ratio 2. Now, once you look at this, so there will be a, here is the Mach number 1, this side it would be Mach number 2. So, the downstream Mach number which is Mach 2. So, the downstream Mach number, that m2 one can calculate like m2 square, which would be gamma minus 1 m1 square plus 2 2 gamma m1 square minus gamma minus 1. Now, all this relationship, this can be also kind of, for the critical condition, it can be reduced to all that thing. So, now at critical conditions, what we can write, that P by P star, that would be gamma plus 1 by 1 plus gamma m square. Then we have T by T star, which would be m square gamma plus 1 whole square 1 plus gamma m square whole square. So, where assuming m1 is that thing, then similarly T naught by T naught star, they should be 2 1 plus gamma m square by 1 plus gamma m square, which is whole square, into 1 plus gamma minus 1 by 2 m square. And similarly, P naught by P naught star, this can be written 1 plus gamma by 1 plus gamma m square into 1 plus gamma minus 1 by 2 m square by gamma plus 1 by 2, which is gamma by gamma minus 1. And finally, the rho by rho star, that is 1 plus gamma m square by 1 plus gamma, which is m square. So, these are the conditions that you can obtain for Rayleigh equations. And just I would like to touch upon this thing. The reason is that when we will be dealing with the compressor, then combustor, the flow field inside the combustor could be treated like that, where there would be flow with some sort of an heat addition. So, now some last quick comments on some of the other factors which would be important. One is we just talk about little bit of standard atmosphere. So, when we talk about the standard atmosphere, now we know when the flow or for a fluid in rest without any shearing stresses, any elementary fluid element will be subjected to two types of forces. One is surface forces, which is due to pressure, and that is number 1, and number 2, body forces, which is essentially equal to the weight of the fluid element. So, that means when we do the force balance, so the force balance can give us this following relation, that delta P is minus gamma k bar, where gamma is the specific, here this gamma is written as the specific weight of fluid. So, this is not the gamma of here, and k bar is the unit vector in the positive vertical direction, which means this is opposite to the gravitational force, and what we can then write, gamma is rho g. So, thus what we will have, del p by del x would be 0, del p by del y would be 0, and del p by del z would be minus gamma, which is minus rho g. So, these first two derivatives here, they show that the pressure does not depend on x or y. So, as we move from one point to another in a horizontal plane, in a x y plane like this, let us say x y plane like this, then the pressure does not change. P only depends on z, and so this particular equation we can write in an ordinary differential equation like dp by dz is minus gamma is minus rho g. So, this is a fundamental equation when the fluid is at rest and can be used to determine the pressure change with elevation or height. And this particular equation, this indicates that the pressure gradient is in vertical direction. Okay. So, and that is negative. So, that is a very important information that this is when you go in the vertical directions, that is where you feel the pressure gradient, and that is also negative. So, which means the pressure actually decreases as we move upward. That means, from the sea level as you go up, the pressure actually decreases in a fluid which is at rest. Okay. Now, for the Earth's atmosphere, where the variation in heights are large or something on the order of thousands of feet or kilometer, so we need to pay some attention here, that how this variation actually occur. Now, in doing that, we can consider the air to be perfect gas, this can be considered. Ideal perfect gas rather. So, ideal perfect gas, and also the equation of state P equals to rho what can be used. Then and what we can write, this dp by dz equals to g p by RT. So, this is using P equals to rho RT. So, if we separate the variables and integrate, so this would look like from P1 to P2, which is going to be L1 P2 by P1 minus G by R Z1 to Z2 dz by T. So, here this R, G and R are assumed to be constant over a range of elevation. So, otherwise they cannot be taken out of the integration and do this integration. So, this actually provides the variation of pressure in Earth's atmosphere. Now, ideally one would like to have a measurements of pressure versus altitude over specific range of altitude. So, measurements for a specific range of altitude. However, this kind of information is usually not available. So, thus a standard atmosphere has been determined and that can be used for the design of aircraft. Now, this was this concept of standard atmosphere. This was developed in 1920s, and since then there are many US and international committees and organizations have pursued and developed such standard. But the currently accepted atmospheric standard is the current one is based on report published in 1962 and then later updated in 1976. So, which is so called US standard atmosphere. Okay. So, that is sort of an idealized representation of the middle latitude with year round mean condition of Earth atmosphere. In that particular chart, what one can see, this is let us say minus 100, 80, 60, 40, 0, 20, this is 0, 10, 20, 30, 40, 50, so this is altitude, that is Z in kilometer, this is temperature in degree C. So, up to certain range of this and this, so this is known as this is zone 1 and let us say this is zone 2. So, zone 1 is troposphere and zone 2 is stratosphere. So, the somewhere the curve looks like this, then it goes like that and like this. So, this is at P equals to 101.3 kPa, which is absolute at 15 degree C. This is at 11 kilometer. P is roughly 22. This is something at 20.1 kilometer. 5 kPa. This is 32.2 km. P is 0.9 kPa. 47.3 kilometer. P is 0.1 kPa. So that's the kind of variation with the altitude one can find. So there are troposphere and stratosphere. So what one can use the temperature variation like T is Ta minus beta z. So Ta is a temperature at sea level, or let us say Z0, and beta is the sort of lapse rate, a rate of change of temperature with height. Then you can find out. Now, these particular equations if we use along with the previous equation, so what we get, that pressure is Pa 1 minus beta z by Ta to the power z by beta r. So again Pa is the absolute pressure at Z0, and then one can find out. Now for the atmospheric layer between 11 to 21 kilometer, so temperature has constant value. This is a isothermal conditions, and then the again the pressure elevation relationship, which we can write just P naught exponential minus z z by z naught by r T naught. So that is what one can use. So P naught, T naught, Z naught are the pressure, temperature and altitude of lower edge of the atmosphere, and then in the higher edge one can find out. So you can form a table like that. So this is how one can see the essential parameters like this, and this is where let us say this is 0, 20 degree, 40 degree, this is temperature, this is minus 20, minus 40, and altitude in some kilometers in this side. So typically this is where your helicopter works, this is some low transport aircraft, this is somewhere above, this is around somewhere 11 kilometer or something, this is where the civilian aircraft, and then top of that fighter. So this is the typical picture, and if you see the with the Mach number and the altitude, so that is what the another envelope you will get. This is Mach number, which would be close to let us say 0, where there is a curve, then 1, then 2, and this is 15, 30, 2, 50, these are in altitude kilometer. So low range here again your helicopter, piston engine, turbopropeller, then you get turbofan, then military fighter, ramjet, then commercial jet works between 65 to 80, then you have other fighter jet which is. So this is another envelope which you will get. So one can see that the this atmospheric variation with temperature and pressure, which are also important for aircraft design. This is also just to give you an idea, because this would be sort of required when we will do the analysis for the cycle analysis or the performance analysis. So we will pretty much completes some of the fundamental discussion on compressible flows and fluid mechanics. So, we will continue with the performance in the next session.